Hey everyone. My passion is working with inverter circuits and other electronics that support solar energy systems. Selling my devices and circuit designs is actually how I pay my bills, so I'm always pushing myself to improve my designs every single day. Today's circuit is one of my latest creations. It's a sine wave inverter that can operate with input voltages ranging from 12 volts to 72 volts, delivering up to about 6 kilowatts of output power. Its peak efficiency reaches 96% at around 1 kilowatt load, with an average efficiency of 94% across the full range. A huge thanks to JLCPCB for sponsoring the PCB for this project. Ever since I discovered JLCPCB, making circuit boards for my projects has become incredibly easy. In just about a week, and for only a few dollars, you can have high-quality PCBs ready for your build. What's even better is that they're super generous, often giving out discount coupons worth up to hundreds of dollars. Ordering is a breeze. Simply create an account using the link in my video description, then upload your Gerber files, preview everything with their 3D viewer, and hit place order. The PCB for this project cost me just $5, plus earn 50 cents for shipping. That's cheaper than a cup of coffee. If you've got a moment, don't forget to check out JLCPCB's website and Facebook page. They often run fun mini-games where winners can score some awesome discount coupons worth a lot. This is one of my commercial projects. If you'd like to buy it, just reach out to me on Facebook. I'm also sharing the project files, but this version has a few minor features trimmed down, like automatic battery voltage detection and fan speed control based on temperature. Like many other inverter modules, I use 10 ohms gate resistors and FR107 diodes. The diodes help the MOSFETs turn off faster during switching. I'm using 140 amp MOSFETs with an 85 volt VDS rating. If you use different MOSFETs, you might need to change the gate resistor accordingly. The capacitors in this circuit are extremely important. If you use low-quality ones, they can heat up and even explode under heavy load. I'm using capacitors salvaged from old equipment, and through testing, they actually perform better than many new ones on the market. You'll need 6 2200 mFarad capacitors rated at 63 volts. Next up are the MOSFETs. I went with brand new ones rated at 85 volts and 140 amps. With 24 MOSFETs, this circuit can easily handle up to 6 kilowatts at 48 volts. You really shouldn't try to cut costs by using old MOSFETs. Sure, they're cheaper, but you'll waste a lot of time testing and matching them for consistency. Plus, since they've already been in service for a long time, there's no guarantee they'll keep running reliably. Here's the completed module. Don't forget to solder 3mm copper wires onto the high current paths. At full power, the current can exceed 100 amps. The heatsink is also a very important part. Whether the device runs stably or not depends partly on it, so make sure to choose one that matches the size of your circuit. The MOSFETs are mounted directly onto the heatsink without any insulation pads. Finally, it's time for the test run. I've connected the circuit to a 5 kilowatt 48 volt transformer, and the results are pretty impressive. Efficiency reached 96% at a 1000 watt load. The MOSFETs, capacitors, and transformer all stayed cool. In the next video, I'll be testing it with batteries and pushing the power to the max. Stay tuned.